Buckle up, cosmic dreamers, as we dive into the awe-inspiring saga of how planetary systems are forged in the fiery crucibles of the cosmos, birthing worlds from stardust and chaos. Welcome to an electrifying journey through the universe's grandest construction sites, where we'll unravel the intricate processes that transform swirling clouds into vibrant planets, moons, and asteroid belts. What sparks the creation of these celestial masterpieces? How do rocky worlds like Earth and gas giants like Jupiter take shape? And could alien systems hold surprises that redefine our place in the stars? Get ready for a thrilling adventure packed with cutting-edge science, dazzling discoveries, and cosmic wonders that will keep you captivated from the first spark to the final orbit. Let's explore the formation of planetary systems and discover how worlds are born together. Imagine a vast, dark void, billions of years ago, where a massive cloud of gas and dust drifts silently in the depths of space. This molecular cloud, stretching light years across, is a nursery waiting to ignite. Suddenly, a shock wave, perhaps from a nearby supernova or a stellar collision, ripples through, triggering collapse. Gravity takes over, pulling the cloud inward, and in its heart, a star is born, surrounded by a swirling disk of leftover material destined to become planets, moons, and more. This is the story of planetary system formation, a universal process that sculpted our own solar system 4.6 billion years ago and continues to craft worlds around distant stars. It's a tale of chaos and order, where gravity, chemistry, and physics dance to create the diversity of planets we see today, from scorching rocky worlds to frigid gas giants, from icy moons to asteroid-strewn belts. As we embark on this cosmic odyssey, you'll see how our solar system's birth mirrors processes unfolding across the galaxy, revealed by telescopes, simulations, and missions that peel back the universe's secrets. Doesn't the idea of worlds forming from cosmic dust make you eager to uncover how it all begins? The formation of planetary systems starts with the molecular cloud, a cold, diffuse region of mostly hydrogen and helium, laced with traces of heavier elements, carbon, oxygen, nitrogen, and metals, forged in ancient stars. These clouds, often 100 light-years wide and containing thousands of solar masses, are stable until disturbed. A supernova's blast, a passing star's gravity, or galactic density waves can compress the cloud, initiating collapse. As it contracts, conservation of angular momentum spins it faster, like a figure skater pulling in their arms. The central region densifies, heating to millions of degrees until fusion ignites, birthing a protostar. Surrounding it forms a protoplanetary disk, a flattened, rotating plane of gas and dust, typically 100 to 1,000 Australian dollars wide, $1 being the Earth-Sun distance of 150 million kilometers. Observations of young stars, like those in the Orion Nebula, captured by the Hubble Space Telescope in the 1990s, show these disks, glowing in infrared from warm dust. By 2025, the James Webb Space Telescope's infrared images of disks around HL Tauri, 450 light-years away, reveal gaps and rings, hinting at forming planets. These disks are the crucibles where worlds take shape, a universal blueprint for planetary systems. How does a chaotic cloud transform into such an ordered stage? Within the protoplanetary disk, planet formation unfolds through accretion, a process where dust grains collide and stick, growing into larger bodies. The disk's composition varies with distance from the star, creating a temperature gradient. Near the star, At 1500 Kelvin, only metals and silicates condense, forming rocky planetesimals, the seeds of terrestrial planets like Earth or Mars. Farther out, beyond the frost line at about $5, where temperatures drop below 150 K, ices like water, ammonia, and methane solidify, enabling massive cores for gas giants like Jupiter. Dust grains, micron-sized at first, coagulate via electrostatic forces, growing to centimeter-sized pebbles. These pebbles clump into kilometer-sized planetesimals through streaming instabilities, where drag from disk gas concentrates particles. Simulations from 2025, using supercomputers at Caltech, show pebbles accreting rapidly, forming 10-kilometer bodies in just 10,000 years. Planetesimals then collide, merging into protoplanets, Moon to Mars-sized embryos, over millions of years. In the inner disk, these form rocky planets. In the outer disk, some grow massive enough to attract hydrogen and helium, becoming gas giants. This process, called core accretion, explains Jupiter's 10 Earth mass core, accreted in 1 to 10 million years before gas capture. Isn't it incredible how tiny grains become colossal worlds? The core accretion model dominates, but gas giants pose challenges. Jupiter and Saturn, with masses 318 and 95 times Earth's, needed rapid growth before the disk's gas dissipated in 3 to 10 million years. The pebble accretion model, refined in 2025 by Leiden University, suggests pebbles rained onto cores, speeding growth. For Uranus and Neptune, slower accretion at 15 to $30 left them as ice giants, with methane and ammonia dominating. Alternative theories, like disk instability, propose gas clumps collapse directly into giants, bypassing cores, especially in massive disks around young stars. ALMA's 2025 images of disks around AB Aurigae show spiral arms, possible signs of such instabilities. Yet, core accretion better matches our solar system's layout, with rocky inner planets and gaseous outer ones. Exoplanet discoveries, like hot Jupiters orbiting close to stars, challenge this, suggesting migration reshapes systems. How do these competing processes sculpt such diverse worlds? Migration is a game-changer in planetary formation. Planets don't stay put. They interact with the disk's gas and dust, exchanging angular momentum. Type 1 migration affects smaller planets, like Earth-sized bodies, spiraling inward or outward via disk torques. Type 2 migration, for gas giants, opens gaps in the disk, slowing migration as they lock into orbits. The NICE model, updated in 2025, posits Jupiter formed at $3.50, migrated inward to $1.50, then outward to $5.20 after Saturn's resonance trapped it, a grand tack that scattered asteroids and shaped the inner solar system. Neptune's outward migration to $30 pushed Kuiper belt objects, forming its resonant populations like Pluto's 3-2 lock. Exoplanet systems, observed by TESS in 2025, show tight-packed super-Earths, suggesting migration-compacted orbits. Migration explains why some systems lack Earth-like planets in habitable zones, their worlds pushed too close or far. Doesn't this dynamic dance of planets make you wonder how our system found its balance? The asteroid belt, between $2 and $4, tells a tale of disruption. Jupiter's gravity prevented a planet's formation, stirring planetesimals into high-speed collisions that fragmented rather than merged. Ceres, a 940-kilometer dwarf planet, and Vesta, with its basaltic crust, are survivors, studied by Dawn's 2011 to 2018 mission. The belt's low mass, 0.0005 Earth masses, reflects this chaos, with most material ejected or accreted elsewhere. Kirkwood gaps, cleared by Jupiter's resonances, show its influence. In 2025, Gaia's astrometry maps asteroid families, like Flora's, from ancient collisions. The belt's C-type carbonaceous and S-type silicaceous asteroids reveal the nebula's gradient, volatiles farther out, metals closer in. Water and organics on Ceres, detected by Dawn, hint at life's ingredients. Could these relics have seeded Earth's biology? Beyond the belt, the Kuiper belt and Oort cloud form from scattered planetesimals. The Kuiper belt, 30 to 50 Australian dollars, hosts Pluto and Eris, with icy composition studied by New Horizons in 2015 and 2019. The Oort cloud, a spherical shell at 2,000 to 100,000 Australian dollars, births long-period comets like Hale-Bopp. Both formed as giant planets ejected ices outward, with 2025 JWST data on comet Bernardinelli-Bernstein showing pristine methane. These regions, less altered than the asteroid belt, preserve the nebula's outer chemistry. How do these distant realms connect to our origins? Moons and rings add complexity. Gas giants' moons, like Jupiter's Galilean satellites, form in circumplanetary disks, mini-versions of protoplanetary disks. Io's volcanism, Europa's ocean, and Ganymede's magnetic field, studied by Juno in 2025, show diverse outcomes. Saturn's rings, icy particles from disrupted moons, evolve via collisions, observed by Cassini. Exomoons, hinted in Kepler 1625b data, may form similarly. These subsystems mirror planetary formation, scaling the process down. What other worlds spawn their own satellites? Exoplanet discoveries, over 5,500 by 2025 via Kepler and TESS, reveal diverse systems. Hot Jupiters, like HD 189733b, orbit in days, suggesting inward migration. Super-Earths, common around M dwarfs, fill habitable zones, unlike our system. JWST's 2025 spectra of TRAPPIST-1's 7 Earth-sized planets show water vapor, hinting at habitability. Protoplanetary disks around young stars, like PDS-70's planets caught forming, confirm core accretion. These systems vary, some lack giants, others have tight orbits, showing our solar system isn't universal. How do these alien architectures challenge our models? Mysteries persist. Why is our system's layout, rocky inner, gaseous outer, rare? Planet 9, a hypothetical 5 to 10 Earth mass world at 500 Australian dollars, could explain Kuiper belt orbit clustering, with Rubin Observatory searches ongoing in 2025. The solar system's low disk mass puzzles, simulations suggest more material, lost to ejections. Interstellar objects like Oumuamua, detected 2017, hint at ejected planetesimals from other systems. Could life seeds, like amino acids on Ryugu from Hayabusa 2's 2020 samples, be universal? These questions fuel research. Future exploration excites. Rubin's 2025 to 2035 survey will map KBO's, hunting Planet 9. Psyche mission, arriving 2029, probes a metallic asteroid. JWST and ALMA study forming systems. Breakthrough Starshot's light sails aim for Alpha Centauri's disks. If we find forming worlds, we'll refine theories, perhaps confirming life's ubiquity. What does planetary formation mean for us? It links our Earth to cosmic processes, forging planets, moons, and life's ingredients. From nebulae to now, curiosity drives us. We're stardust, shaped by universal laws, exploring our origins. As we near the end, let's gaze ahead. The formation of planetary systems, birthing worlds from chaos, unveils creation's blueprint. New missions, data, and dreams will illuminate it. What worlds form now? How will they shape our cosmic view? The universe beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into the formation of planetary systems, how worlds are born. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about planetary formation? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Dreamers.